All right, I saw the notification. Okay, so today we'll be hearing from two speakers. First up will be Mainak Singha. And I'll just also note that if you have any questions during the talks, feel free to write them in the chat, and then we can read them out at the end of the talk. So Mainak is a PhD student at the University of Manitoba. He's working with Professor Chris O'Day and Professor Steffi Baum. His research interests are in AGN-driven outflows, jet ICM interactions, and imaging. His dissertation aims to answer the following questions. Where are the outflows launched from, and what is the mechanism that drives these outflows? Mainak's research is supported by the Kanji Award at the University of Manitoba, and then he holds a master's degree from the University College Dublin, where he studied as a global graduate scholar. So if you want to go ahead and share your screen, Mainak, the title of his talk will be Compact Radio Jet is in Action. Here we go.
Perfect. So, hi everyone, and thanks Amy for the great introduction. I'm Mainak Singha, a PhD student at the University of Manitoba, and today we'll be talking about the compact radio jet-driven outflow in a radio-quiet quasar. So now, many massive galaxies hold supermassive black holes at the center of their host galaxies. These black holes grow through mass accretion and are visible as active galactic nuclei, or AGN, at the center of the host galaxies. On screen, you can see a schematic diagram of an AGN. At the very center, we have supermassive black holes, and then till 0.01 parsec, we have the accretion disk. Further out till 0.1 parsec, there exists a broad emission line region, or the BLR, where the highly dense gas, the electron density, I believe, is around 10 over 10 to the 8 per cubic centimeter, where the high velocity gas of like a few thousand sub-kilometer per second is orbiting the black hole, and the spectral shapes of the emission lines originating from this region appear broadened due to Doppler effect. And then further out till 10 kiloparsec, up to we have the narrow emission line region where the ionized gas is relatively at rest, velocities of a few tens to a few hundreds kilometers per second. And then you see also like a dusty donut-like structure on the screen, which is called the torus, which is kind of surrounding the broadline region. Now, if you happen to look directly into the torus, as the torus is showed in the broadline region, you cannot actually see the broadline region because the torus is blocking it. So what happens that in the spectral shape, you see only the narrow emission line region features, for which we call them like a type 2 AGN. And when you're looking from an angle where the torus is not blocking your view, you get to see the broadline region and all the broad emission line structures in the spectral shape, and they're called type 1 AGN. Now, it's been largely debated whether these AGN just sit at the centers of their galaxies and accrete materials. It was not until the discovery that explains the bright end of the galaxy luminosity function. On the faint end, you see that the both ionizing photons emitted by the first galaxy supernova explosion reduces star formation efficiency, which actually explains the fainter end. But the cold dark matter model and the reionization and the supernova feedback cannot explain the brighter end of the galaxy. Like, why are there so many massive galaxies there's so few massive galaxies seen than predicted? So in order to explain this discrepancy, theoretical studies proposed of the idea of AGN feedback, where the radiative and the mechanical energy from the AGN play crucial role to regulate the growth of their host galaxies and the growth of themselves in this process. Now, primarily, there are two routes of AGN feedback. On one route, the AGN launches galactic scale outflows that expels the gas out of the host galaxies. On the other hand, the mechanical energies of the radio jet from the AGN could reheat the environment. Now, outflows are like really complicated. Now, for the outflows, there could be a situation where the radiation pressure from the accretion disk could also drive the outflows, as you see in the bottom left figure of the middle panel, as well as the radio jets in the top left figure of the middle panel. Now, the jets can not only shock the gas due to like the Bohr shock the gas and push them away, as you see in the left panel of the bottom left in the right image, but also they can entrain the gas. It's been kind of dragging all the gas along with them as they're traversing out of their host galaxies. So this process is called as entrainment. Now, this is the scenario where you have powerful prominent radio jets, but a lot of the AGN, they show like almost very little emission in radio, the radio quiet agent, what launches the outflows, and what are the mechanisms of the feedback. In order to answer these questions, we established the Close AGN Reference Survey, or CARS, so which consists of 40 type 1 nearby radio quiet AGN. So the fact that we have nearby AGN, we can basically study the 1 arc-second scale less than at sub-kiloparsec regime. And also their bolometric luminosities from like 10 to the 43 to 10 to the 46 arcs per second. So like they're like fairly luminous AGN. So we can at least study the AGN driven activity in like a really high detail. And also CARS is a multi-wavelength survey. So we have data from XMM Newton, Chandra X-rays. Then in optical, we have all the integral field unit like MUSE, the multi-unit spectroscopic explorer, then the VMOS and PMAS. And then also we have in radio, the very large array VLA, and then going to further higher angular resolution, the VLBI, the very large baseline interferometry, and then the ALMA, which traces all the molecular gas. So having this amount of extensive data, that enables us to like study this AGN in really high detail. Now, as we're going to talk about the alphas in radio quiet quasars, we've got AGN, where I just want to briefly mention 2 notable studies from our CARS survey, which is the most relevant. So in 2019, we wrote a paper on the Agent Galaxy HE1353, where we see that the radio emission is co-spatial with the outflow. So we only had VLA, L, and X-band observations, and it was almost near impossible to get an estimation of an opening angle from that data. So just by looking at the morphology, we did conclude that like that's a radio jet driving the outflow. So that's again a radio quiet AGN. It's not your radio loud agent where you see like prominent radio jet. Now in 2021, we wrote another paper that focuses on the entire outflow aspect of the entire CARS sample. So what we find that, so we not only find that the agent-driven outflows are actually unresolved by the MUSE IFU. So we're talking about an IFU which is a pixel size of like a 0.2 arc second per pixel, like a really high angular resolution. And we're actually looking at like quasars of like almost redshift 0.04. So the fact that the outflows are also for most of the part, they're unresolved, they're already giving you an example of like what kind of spatial scale they could consist of. So they are about like a less than 1 kiloparsec scale. So they're definitely not reaching out to whole scale galactic scale. Also, we find that not only all the AGN launch outflows, but they are actually launched from a region which is less than 100 parsec from the central engine. So the 100 parsec scale is definitely not your accretion disk scale. As I was talking, that accretion disk is about like 0.01 parsec. So that already gives you an indication of like where the outflows could be launched from. And also what we find in addition to like the previous results, all the outflows which are either compact or like a less than 100 kiloparsec, and like a few extended, like maybe over several kiloparsec, they all have similar AGN luminosity. Well, if the AGN luminosity was responsible for launching the outflow, the one would expect that like the luminous the AGN get, the outflows could be like much more extended, but that's clearly not the case, as we see in the figure. So like the fact that we're already having a radio emission overlap co-spatial with the outflow, and the fact that the outflows are not driven by the accretion disk properties already gives us an interest that maybe the radio emission could be responsible to launch these outflows. To investigate that, we focus a particular AGN called HE00401105, which is the main topic of the discussion. So we find that this outflow is like a really compact, again, unresolved by Muse. So it's like a diameter of like less than 700 parsecs, and it's launched from 91 parsec away from the central engine. So the reason we chose that was like this was the largest offset between the launching point of the outflow and the central engine. So we also note that this is a really fairly highly accreting AGN. So like we're Eddington ratio like over like 0.04. So it's not like your lower excitation radio AGN, which are like relatively inefficient. This is a relatively efficient AGN, and we're seeing such a compact outflowing feature. So that itself makes it an exciting target to study the mechanism of the launch point of the outflow. If we took the other examples, it gets just worse here, because like the outflow, the center of the launch point of the outflow gets to like 10-20 parsec away from the central engine. So this is the fact we chose the this object is solely because it has such higher offset of the launching point from the central engine. Now, what happened that we already talked that the outflow is compact. So previously when we analyze the outflow, we were basically focusing on the O3 high ionized gas. And also we were focusing on the approaching side of the outflow. Now, if you think about the biconical model of the outflow, it also does have a receding side. So we did not take that into account before, because the O3, the approaching side of the outflow was so bright. So what we did this time, that we also checked that there is another outflow in H alpha that is also unresolved by Muse. So we basically subtracted all the unresolved emission from the broadline region and for the approaching side of the outflow. So now we are left with all the residual faint emission, and then we modeled that with like a 1 to 2 Gaussian component. Why we took another Gaussian component? Because the fact that we see the receding side of the outflow right on the eastern side of the nucleus, and we see that it's creating kind of semi-cell-like structure, but it's just not fully covering the range because you have the approaching side of the outflow here. So some kind of crosstalk is happening between these two components. So, so what we do is we basically create all their emission and kinematic profile, and we then model their kinematics. For H alpha, we see like a really nice gradient-like structure, which agrees with your pure gravitational motion, because it's expected, because you also have the star formation that's illuminated in H alpha. But for O3, the model fails miserably. Like it's entirely different, like not a smooth gradient like H alpha you see here. So when the model tries to fit it, it just returns with high residual. So what does it mean in a physical sense? That like in the O3, there is definitely non-gravitational motion dominant, and also not only non-gravitational motion is dominant in the small scale where you see the outflow, but also in the entire nebula. And when we're analyzing those, we're just basically taking account of all different ionization for the part of the host galaxy, which is being powered, maybe powered by something. Now to get the something, we introduce our VLAC 5.2 gigahertz and 10 gigahertz observations. Now, Coming back to the receding side of the outflow, we did see that its one-dimensional profile matches exactly with the PSF until it gets cut off because we have the other approaching side of the outflow. So what we do is taking on the PSF, we do a deconvolution, and we find that the center of that receding scale of the outflow is about 600 parsec away from the central engine. And it's about like creating a shell-like structure. It's about, and the thickness of the shell is 250 parsec. And it's about 1.5 kiloparsec wide. And also interestingly, we see that here's you have the central engine, and then you actually have the launching point of the H alpha outflow, like which is 29 parsec away from the central engine. And then farther out, you have the O3 outflow, which is like about 91 parsec away. So something the weakly ionized region is closer to the central engine and also lies on the radio emission than the highly ionized. So maybe like now one can probably, that's the question we're trying to ask, like, is it kind of tracing out the different different region of ionization on the path of the radio emission? So, and this feature is not only see in C-band, but also you see in high frequency radio observation. So like that's actually happening, and that's like really tied to like the central 200 parsec regime of the AGN. Now we focus on the mechanism of the blue wing, which we are seeing before, the approaching side of the outflow. So we compare that with the shock model of Allen 2008, and we find that this ionization mechanism is most consistent with shock ionization than photoionization. And like we find like a shock speed of like about 1,000 kilometers per second. So, but for the rest, they're mostly photoionized. Now you can me ask a question, well, if the central blue wing is shock ionized, why even like the red shell is photoionized? It could be due to like as soon as the outflow is being launched, it just for the receding side, it faces the ionization cone of the AGN and it gets illuminated by the AGN, which basically puts in the ionization diagram as it's to be photoionized, when in reality, it may not be actually photoionized, just being illuminated by the AGN. Now, we even aim for even higher angular resolution to find out what's the radio structure it is, because a radio structure that's overlapping with the outflows in both the both C and X-band observations is definitely what interesting. So what we find that the brightest hotspot in our VLBI image basically coincides with the AGN location, and then one of the fainter hotspots actually refer to the H alpha, the launch point of H alpha, and the other one, and then the other one for the O3, that's almost co-spatial with another brighter hotspot. So this error bars here, we take count of all the astrometric uncertainties along with the systematics, and the error bars correspond to like the 3 sigma. They're not like 1 sigma, just to make sure that like whatever positions we're having, they're within this region. So now people can say, well, these are just kind of faint, they may not be really reliable. Well, we have the brighter hotspot, and what I do is like just to get an estimation of the upper limit of the underlying source, I we added them the two extremities and calculate that the hub opening angle here is about 8.9 degrees. Now note that like this is actually convolved with the beam. If you deconvolve that, the underlying source size will be like even smaller, and then the angle subtended would be even smaller. So this is the maximum, this is a kind of max upper limit of the hub opening angle. Now, if we compare that with like a Mojave survey with like a Blazer jets by like Pushkarev and Kovalev 2013, they had then almost hub opening angle for the Blazer jets to be 10.5 degrees. And the fact that the hub opening angle here is about 8.9 degrees that already implies that could be a radio jet. And this now we just basically overlay our EVN image with the VLA to see that like this is a hint that the radio jet is driving the outflows, because like they are not only co-spatial, and the highly collimated nature of the radio emission confirms the jet nature, and that's what we saw before in the VLA images, which is just only manifests itself in a better way in our VLBI image. Now we talked about what was causing the outflows. Now for the impact, there are several literature studies that talk about, well, there are compact radio jets could cause large turmoil of like line with gas line width of like 900 to 200 kilometers per second. But when we look at our own HE004 kinematics, after doing a lot of deep blending and deconvolution, a lot of processing of the data, we are left with really quiescent kinematics. So like what's happening here? So the issue with those studies were before, like they did not actually take account of the AGN induced emission. They did not subtract the extreme kinematics that AGN could produce. And if you don't take count of those kinematics and do all the deconvolution like the procedure we followed, the AGN induced central kinematics could be apparently seen in the spectra much farther out than their actual spatial dimension. And that's what's happening. But for us, we do not see that because we already subtract all the bright, emission, which are most centrally located, which is the reason we are seeing all this quiescent kinematics. So the fact that the jet is about 200 parsec wide, it cannot actually turmoil the gas in like a few kiloparsec scale in the host galaxy. It does affect the gas motion, but only it transfer like a really little amount of energy without creating large turmoil in the interstellar medium. Just to conclude that, we find that in these radio quiet quasars, the radio emissions are overlapping with the launch point of the outflow in both C and X-band image. And using our VLBI data, we find that this highly collimated nature of this radio emission confirms its jet nature. And in contrary to the other previous studies, we find that the ionized gas kinematics is like fairly quiescent. And this is important that you should take the beam smear into account. Otherwise, you'll end up with really high, apparently high ionized gas kinematics, which are not physically extended to like 1 kiloparsec scale. They might be much more central located. So thanks very much for listening, and I'll take the questions.
Perfect. Thank you so much, Mainak. If any questions, please either raise your hand or post them in the chat. Okay, give another.
Quiet group. This is Randall Smith. I'll just ask one basic one. So where do you head next? What's the next project that you'll be doing with this?
Oh, so we are currently working on like 3 different papers. So we already found that the outflows are actually related to all the the radio emissions. So we're trying to establish like a universal connection between all the radio jets and the outflows, and also working on another project called the Hercules A, where we find that the gases being entrained by the jet. So yeah, we have so many projects that's happening, and heading next, I guess like I'm probably going to apply for postdoc soon. So in the States.
That's great.
Very good.
It looks like we have another question from Pratik. Go ahead.
Hi, so nice talk. How did you estimate the Eddington ratio? You mentioned they're quite high, 0.04. Was that estimated by you or from previous studies?
Oh, this was estimated by us. So like basically we had the volumetric luminosity for the AGN, and we already had the Eddington luminosity calculated for our CARS DR1 paper. So the volumetric luminosity we did calculate using the H beta luminosity, the broad line H beta luminosity, as the O3 is much more not like a good estimator for the AGN. So yeah, just basically divide the volumetric luminosity, the Eddington luminosity, and
that
the
one.
Eddington ratio.
Cool.
Okay. Any last questions for Mainak? All right. If not, we'll thank Mainak again for that great talk. So let's do our little clap emoji here. And next we'll move on to Pratik Dabhade. So Pratik is a postdoctoral fellow. Change my screen here. Okay. So like I said, Pratik is a postdoctoral fellow at the Observatory of Paris in France. He completed his PhD from the University of Leiden in Netherlands in the early 2021. This was after he completed his Bachelor of Physics from the University of Mumbai and his Master's in Physics from the University of Pune, respectively. So he was a Indo-French CIFRIPRA fellow at the IUCAA Pune from 2015 to 2018. He specializes on the topic of giant radio galaxies and works on AGNs and galaxy clusters using radio telescopes, along with other available multi-wavelength data. So today he's going to be talking to us about decoding the largest radio galaxies in the universe. And with that, Pratik, I'll hand it over to you.
Thanks, Amy. Thanks to organizers for giving me a chance to speak about this work. So I'll be talking about giant radio galaxies, which are the largest radio galaxies. And so these are this refers to a subpopulation of radio galaxies which grow to megaparsec size. And the way we define them is if a radio galaxy grows beyond 700 kiloparsec, we refer them to as the giants. They can at times grow to sizes of galaxy cluster, about 5 megaparsec. That's the largest found so far, mostly hosted by giant ellipticals with FR2 kind of morphology. And naturally, they host the most biggest astrophysical jets. So just to give you a comparison, when you stack 33 of our Milky Way galaxies, that what gives you a megaparsec. So it's a huge scale which we are talking about, to which these grow. So these were discovered in the early 1970s with the Westerbork radio telescope. And with recent advancement, we have better view of them for many such systems. To show you how your favorite radio galaxies like the Cygnus A, Hercules A scale against the biggest giants. This is just a comparison. And these are unique with respect to their size, and hence they can be probes for many other processes like these cluster relics, which are seen only in the radio band, where the shock is propagating and the radio emission traces it when two galaxy clusters merge. And these have been also used as a probe for WIM, which you all know about, and to probe the missing baryon problem. There have been few studies to also use them to measure the variation in the foreground rotation measure of the galaxy, and to obviously, since they grow to so large scale, even probe IgM. So what are the open problems related to giants? So why do we want to study them apart from using them as these probes? Is because we want to understand why they are so big. How are they formed? Are they really rare? How do they contribute to other processes? Are they just the older counterparts of radio galaxies? Do they have recurrent activity going on, enabling them to grow to larger scale? And how are their jets so stable for such large distances. So is it that they are hosted by powerful AGN, or they are growing only in sparse environment without any obstacles, or is it a combination of two? So for that, we need to gather more sample and perform a multi-wavelength, multi-frequency study to address some of these questions. And the way forward is to find more of these giants and perform spectral aging studies and their AGN, study their AGN in multiple wavelengths to understand their properties, and to study their large scale environment to determine what kind of environment they're growing and which is probably helping them grow to such large scale. So therefore, we came up with this project called Carl Sagan. Nothing to do with this great man, but it's acronym for search and analysis of giant radio galaxies with associated nuclei. So here are some of the goals which we set out for our project: to make a complete compilation of all the giants, which was not there when we started this in 2016, to look for more giants, to have a bigger sample, then make complete samples, and then study their AGN as well as large-scale radio properties and environmental properties. So this is where we stood in back in 2016 when this started off. This project, only about 300 were known. So we set out to dig the literature for finding more of these giants which were reported, and it was a mess because there's no catalog and there's no nomenclature set for this. People used to refer them to various names. So also in the older days, the poor resolution and somewhat poorer data led to some misclassification as well. So we had to re-verify all of them. We uniformly measured their sizes, angular sizes, and then used updated cosmological parameters from Planck, because in the 70s, as you all know, the H0 was used as 50 or 100, various, depending on the models, used back then. So we continued this till mid of 2020. And just to give you a summary of, just a brief summary before I get into the results, these are some of the papers which came out where we have reported new giant as well as the study which we have performed using various telescope, and some upcoming papers. So we performed a very systematic search through new and old surveys, and this was done in a semi-automated fashion. And we required not only the radio surveys, but also the backing of optical surveys, which was very crucial. So first we used the LOFAR 2-meter sky survey. That's a survey with International LOFAR telescope at 150 megahertz. And it has achieved very unprecedented sensitivities and resolutions of around 5 arcsecond. With now we are having much better figures of 70 microjansky. So as a result, we performed searches over 424 square degree area in the Headache field, and we found a very large sample, to our surprise, of around 239 giants, of which 225 were new. And this was not expected, but we were quite lucky to have the sensitivities which LOFAR allowed us to get to. So that also enabled us to map their morphologies and understand how their jets are propagating. Are there outflows on very large scales? And we also got some with the hybrid morphology, where you have FR1, FR2 on the other side, and the restarted double. So mind you, these all are on the scale of megaparsec. So these subcategories are rare in themselves, and they're giant as well. So we also used the existing older surveys which cover a bigger part of the sky, like the NBSS and the TGSS. There are two different frequencies. They complement each other and also help us to get a spectral index. So with a lot of database matching and verifying, we finally found another big sample of 162 giant radio galaxies, and that's reported in the first main paper of SAGAN project. So a snapshot is shown of the same here. And so after 4 years of this work being carried out, this is where we stood. We doubled the known population of giants and made a catalog of 820 such sources. So that's the biggest known to date. Now that we had this catalog, we could finally ask these important questions about their space density, excitation type, and how their properties compare with the smaller sized radio galaxies, and if they're old or not. So that brings to our third part of the project. So we use the WISE diagnostic to color plot to initially classify the agent types. Is it high excitation, low excitation? So as you can see, they don't have a preferred accretion mode. They are there in high as well as low. So the WISE mainly was used because getting spectroscopic data for all these was not possible. We were limited to what was presented from SDSS. So to go beyond, we had to use this diagnostic, which works quite well for such classification. Along with this, for all these sources, we computed the radio powers using the fluxes at 2 frequencies, the spectral index, to understand how old the source is in a broad fashion, their jet kinetic power, black hole mass, Eddington ratios, and identification of the giants in galaxy clusters. And we created subsamples, matched them in Redshift to do this kind of comparative study. So first we took the giant radio galaxies hosted by AGNs and the others hosted by quasars and compared their properties. And we found that the quasars, as expected, were more luminous and had higher jet power and much flatter spectral index, indicating the ongoing activity in the AGN. Next, we also compared the properties between the high excitation giants and the low excitation giants, and to see what is making them different or similar. So like the GRG-GRQ, here also the high excitation were found to be more luminous and with higher jet power, and also showed the higher Eddington ratio. So these properties were not known prior to this kind of study. People had just a few assumptions what could be going on, but with the large sample which we found, we were finally able to show. Now these properties are very analogous to their smaller sized radio galaxies. So next we tried to compare the black hole mass and the Eddington ratio of the radio galaxies and the giant radio galaxies. Here we are limited with the GRG data because of the spectroscopic non-availability of the spectroscopic data. So here we find that they almost show similar distribution. The Eddington ratio shows a bit of difference, but I think with more of this data, I think they'll show a very similar distribution. So we don't find a very contrasting difference in their black hole mass and Eddington ratio distribution. We also tried our hand at trying to see if there is a connection between the kinetic jet power and Eddington ratio, where we try to show the disjet coupling, and we get fairly good correlation when we try to plot them with the volumetric and the jet power with the Eddington ratio and the scaled jet powers. So next was to study the environment, which is equally important to understand if they grow in sparse or dense environment preferentially. So we use the WHL cluster catalog to find how many of them are BCGs, brightest cluster galaxies, lying at the center of galaxy clusters. And we found about 60 of them are hosted by BCGs residing in denser cluster environment. However, we noted that these are avoiding very massive clusters, and these are on the lower end of the clusters. So the environment certainly has an effect on their growth. It is clear. However, they do grow in denser environment given the right AGN push or the jet kinetic power. So it is worth studying these systems in greater length to understand how they're propagating in such environment. So we also carried out a small survey of their host galaxies using the IRAM 30-meter telescope. And we only had proper detection in 2 such systems, and most of them did not have any detection, but just significant upper limit. They do show quenching, that indicates quenching and star formation. So the star formation is quite low, except for this spiral, which is very unusual, giving out massive jets. The third part was focused entirely on giant radio quasars, where we showed the properties of quasars in comparison with the other classes, and showed that the sizes are slightly higher for giant radio quasars. So we also, in this past 4 years, we have also carried out our multi-frequency campaign for studying them at various radio frequencies, so that we will be able to study these aspects to firstly to recover their low surface brightness features, to understand how the morphologies are present in the various environment these giants are growing into, to understand if they are really old compared to radio galaxies. To get spectral ages, we need multi-frequency data. Do their jets show instabilities of any kind? And we can study the stability of the jets, and if there is any presence of hotspot or shock acceleration along it in the knots. So this is a work in progress. So I'll just briefly show you a snapshot of some of the giants we mapped with the GMRT. So we have mapped it at 150, 325, and 610. So I'm just showing you a snapshot of few of them at 610. And you can see how a giant looks at various frequencies, using which we can perform multi-frequency studies to get spectral ages and magnetic field estimates of particular regions. Because of the high resolution, we can now resolve the various component and their ages. So along the way, we find some very interesting objects, and which we need to probe in quite more detail. So this is one such object which we found in NVSS, and we were not able to understand the weird morphology it was showing. So we followed it up with GMRT and then with LOFAR, and found very unique structure that we had a 200 kiloparsec long jet terminating into a kink, omega shaped kink, and then the jet recollimating and blowing up a balloon or a mushroom shaped lobe, which doesn't show any hotspot. So all these properties which I just mentioned, these are very unique, not found elsewhere. The kink, the instability which it might be, is of the scale of 100 kiloparsec. There are hardly any examples in literature showing such this thing for peculiarity. The spectral index indicates that it's quite flat and possibly a tracer for shock. Now this needs to be verified with X-ray observations, with further X-ray observations. To add to the complexity, the host galaxy is hosted by a BCG. So this is residing in a galaxy cluster of relatively low mass. But this is what I was referring to when I mentioned how the high resolution maps complementing the environmental study will help us understand how these grow. So that is the main highlight of the SAGAN project so far, that they are not, GRGs are not so rare as previously we thought to be. They do grow in denser environment, but not very, very dense environment. Their AGNs have both accretion mode, low as well as high. We have seen evidence of the quenching by the jets in their host galaxy, and the spectral ages which we have obtained, and as well as from the literature, they indicate that they are not very different from that of radio galaxies. However, there are caveats which I can discuss if anybody is interested to know more about. So for future, we would like to study especially the giants growing in galaxy clusters to understand the feedback process. Since they're going to megaparsec scale, you can imagine the possible cavities they can be making. And we can probe the environment IgM, possibly look for SZ effect if at all possible with the inverse Compton from X-rays. So the future looks promising. With all these new telescopes, we are going to find more of such exotic objects, and we'll have to be prepared when the data comes. And for that, we need to invest into finding these things in an automated fashion. And we require algorithms. ML is the way, which is now catching up a lot. Or we need to put more manpower. We need to encourage more people to come and join us in this effort. And one such effort is citizen science, which we ought to promote and help out with, and it will help us along this quest of finding and understanding these interesting objects. So thank you. I'll take questions if you have any.
All right, thanks for that great talk, Pratik. So if there's any questions, again, just put them in the chat or raise your hand and we can call on you. Okay, looks like we have a question. Let's see, how do you pronounce this one?
So,
Okay.
thank you for your great talk. Maybe I missed this part, but have you kind of calculated the speed for jet propagation with the spectral analysis? How fast should it be to reach that distance?
Okay, so I haven't done this, but this has been done in prior studies, and people have found jet speeds of about 0.2, 0.3 C. That's usually taken as the mean. There are studies by Scheuer and Hardcastle which have shown this using samples as well as simulation, that 0.2, 0.3 C seems to be optimum speed velocities to get to such scales.
Thank you.
All right, open it up to any more questions. Go ahead, Mainak.
So could you please go back to slide 46, Pratik?
Sure.
So I see that the spectral index is probably, correct me if I'm wrong, it's getting much more non-thermal as you go towards the edges, right? But I was expecting like towards the center, the non-thermal nature would be much more prevalent for like jets. Is like, isn't that like kind of counterintuitive?
So all what you see is non-thermal, right? This is all radio emission, so that's all non-thermal.
But like the spectral index is kind of getting like much more negative, like the alpha is getting like having like much higher value towards the edge.
Yeah, so okay, so
center?
the edge values are not taken very seriously. The ones which are in the center, that's what we take. And also the notation which we are using is S proportional to nu raised to minus alpha. So just remember that the flatter spectral index is expected at shocks, knots, or radio cores or hotspot. But these lobes don't show any hotspot, and it shows a steeper spectral index. So this is roughly about 1.
Okay, that makes sense. Thank you.
No questions in the chat. Any other questions from the audience? Okay. Well, if there's no other additional questions, we will go ahead and thank our speakers one last time for both of their great talks. And we will see you guys next week. And again, you can sign up to meet with the speakers using the link that was sent out if you have additional questions for them. Thank you, everyone.
Thank you so much.